OneNote, right? We don't have to put it in the halg3.
Correct. Yeah, it just goes in your shared OneNote folder. I'll check it directly from there. Mia?
When we're writing, I think it's an infinite it's writing the inequality, and there's infinities in it, that automatically says it's greater than or less than, right? It's not greater than.
Yeah, so involving an infinity, your inequality should always be a strict less than or greater than when appropriate. It can't be equal to infinity because it's not actually a number. Exactly. Okay. Anyone else? Natalie, you had your hand up. Was it the same thing? Sure, that's fine.
For number 8 on your one, what is the range? And I can't read that.
This is the one with the words in it?
Yeah.
Yeah, as long as you're like I'm not gonna be so picky as to like, oh, you didn't spell that quite correctly. If you have like 1 or 2 letters at the beginning, so it's like close to it, that's fine. Like I know I get that the image did not transfer very well and it's quite difficult to read, and zooming in doesn't help because the resolution is pretty bad on the picture that I use there. So as long as you're like, I can tell that you have the right number of things and the first letter 2 is correct of whatever it is, that's good enough. How's that sound? Fair? Okay. Jane? Yeah. So is it a function? Right? If I look, everything in the domain is used and it's only going to one location, so it's a function. So the domain there, I would say, I don't know, that looks like Maria and Amelia maybe. Again, I don't care about the spelling. If you think it was somebody else or whatever, as long as you've got like the first letter right. If you call Joe John or something, like it's fine. No big deal. And then the other one, what's that say? I can't even read that first thing at all. It starts PU something. And then it looks like PowerPoint. I don't know, is that Regal? Tell what that word is. And then handpipe. I don't know what that means. And oral presentation, I can read that. And that's it. That's all we really need to do, is we can just write these, since it's a finite relation. Anything in that mapping diagram is going to be a finite relation because you can't draw an infinite number of arrows. And the arrows are what represent our ordered pairs. So anything kind of in that form we know is going to be finite. And for finite situations, you can just list the items in the domain and the range separately, which is all I would do here for this.
Okay, so for finite relations, you don't have to use set builder.
I mean, technically, this is like a set builder notation. It's just like the simplified version of it. But yeah, you can't write an interval or an inequality because those really, you need an infinite number of items to do that.
Like a line.
Like a line.
You couldn't do that for 8, 9, or 10.
Correct.
Okay.
Yes. And you couldn't have done it for 1 or 2.
Okay. And then, could you explain the difference between set?
Sure. So are you good with interval notation? Okay. All right. So let's just look at number 5 here, and we'll just do the domain. Sound good? Okay. So we'll start with interval notation because that's the one we've used the most in class, and it's probably the one you're the most familiar with. So we'll start with there, and then we'll translate that answer into the other 2 forms. Does that sound fair? Okay. So domain, I'm going to start by identifying the leftmost point on my function. So it appears to be here at 0, 0. You agree with that? Okay. Since we're doing a domain, all I care about is the x. So I'm just going to write the x coordinate for that point. And then the rightmost point would be either of these, but we have arrows going on in both directions, right? So if I think about this as like a point, this is kind of like positive infinity, comma, positive infinity, because I have an arrow going to the right and up. And I could kind of think about this point as like positive infinity, comma, negative infinity, because I have an arrow going to the right and down. Are you okay with that, Jane?
Yeah.
In either instance, what I care about is the x. So that's in infinity, or positive infinity. Okay with that? Now, I know the infinities always get a parenthesis. And then for the 0, I need to decide whether I should get a bracket or a parenthesis there. To do that, what I'm going to do is I'm going to look at my relation, or my graph, or my function, or whatever it is you have, and go, is there a point that actually has the x-coordinate of 0? Well, absolutely. It's this point here, 0, 0. So this should get a bracket. Okay? Now I'm going to translate this into the other two forms. Jane, are you with me so far? Okay. So we'll do the inequality next. So the inequality, I'm going to have 0. And then because it's a bracket, I have less than or equal to x less than positive infinity. So the bounds, the upper and lower, or the lower and upper bound for my interval are the same lower and upper bound for my inequality. Okay? Now turning this into a set builder. So I have this, that. And my rule that I'm going to use is just the same as my inequality. So we have the interval, the inequality, and the set builder. Joe.
Okay, so I know where you got the 0 from.
Mm-hmm.
So, like, why is it positive?
So we're talking about the domain, which is about the x-coordinates, right? So if I look at the far right arrow, I'm only concerned with the x-coordinate. Does that make sense? If I was doing the range, that would be a different story. Then I care about the y-coordinate. Well, the range here, the lowest point is here, and the highest point is there. So it would be negative infinity to positive infinity for the range. Is that okay? Evan, you had your hand up?
Yeah, so when you use a bracket,
So the bracket is the same thing as the or equal to inequality. So because 0 is an x-coordinate in our function, I need to use a bracket. Okay, as opposed to if this was like the same thing, but I had like that open circle there. There I would use a parenthesis at 0 because there is no point at 0, 0.
so it's like an actual point on the graph.
Yes. Yep. So the bracket basically means is included in the set. So the domain is the x coordinates that are used by the function, or we have 0, 0 as a point using that x coordinate of 0, so it should get included. As opposed to this picture where there is no point using 0, 0 because I have the empty circle. Jane.
So for one and two, you can't use set builder or inequality.
So the set builder is what you'd use where you the list.
Oh, okay.
So that is set builder, but you can't write an interval or an inequality for those ones. So intervals and inequalities are only for infinite sets. You can only use to write it down an infinite set. If your set is finite, you just list it. And that is a form of the set builder. Okay? Do we feel a bit better about the homeworks here? If you guys have some more stuff, we can answer some more stuff. But these are good questions that you're asking and the right kinds of questions to be asking. Joe. Number 2. This guy right here?
Yeah.
Okay. So first things first, are you good with function or no?
Oh, yeah.
Okay. So you just really care about the domain and range part?
Yeah, is that just like, is it just like,
The domain is just the x's, and the range is just the y's. But notice the y's are all the same. Do we list that 2 more than once? No. Remember, for sets, we only list something once.
so I know I didn't hear the rest of that. I heard you said you don't have to do the inequality and also like that one, like the graph. So you
you have to do this. What we did is a set builder notation. Okay, what you don't need to do is an interval notation or an inequality. Those are both only for infinite sets. Okay? And I realized I just wrote all over the assignment in the content library that I didn't mean to do. So what should I do here? Do this. Paste it down here. Come on, are you going to paste or not? What are we doing here? Okay, rename this as today's notes. And I will erase all this, I guess. All the homeworks will be due at Sunday midnight. So just because this one was pushed back to Thursday, the other one's still going to be due Sunday, though. So we're not going to change that usual due date. It'll stay the same. Does that sound okay? Okay. Joe, is this a hand or a stretch? Okay, what's up? Well, you've had your first homework quiz already, right? We did that already. The first test is probably maybe end of next week or the week after. Hard to say, depends a little bit on how much we get through and all that kind of stuff and the questions that you guys have and all that. But probably end of next week or the beginning of the week after. Okay? All right. Today, then, we ready for some new stuff? Or to do some content anyways? Obviously, if there's more questions, we can certainly do more questions. Okay. So, to this point, what have we talked about so far? We've been talking about funds, right? We talked about positive, negative, 0. We talked about increasing, decreasing, and constant. Years. Did we talk about Extrema yet? Okay, so that'll be what we start with today. That's fine. Let's do a quick example involving some of these concepts that we've talked about last time, just to kind of refresh our memory. Sound good? So just a little example. Yeah. What did you just do? All right. Call you that. Call you that. That. We'll call this one. Okay. So just to kind of review things a little bit, is this a function?
No.
Why not? Where? Sure. Where is the repeating x value, though? Is it repeated? Okay, be careful. So is this a function? Yes, right? So there is no repeated x values. The place where you thought there was, you notice that one of the points was closed and the other is open. So that x value is really only used once. Are we cool on that? Okay. So we have a function. And we know it's a function because we have no repeat. Okay. What's the domain and range going to be for this function? Maddie? Okay, so this is a finite set of points? No, right? How many points are contained on this graph? Infinitely many, so we probably need to use an interval here. Mia? Good. So that is the domain. Notice the furthest left point is negative infinity, comma, negative infinity, right? The furthest right point here is positive infinity, comma, positive infinity. But we have to be a little bit careful because these two sections of the graph aren't connected in between. Everybody's okay with that idea? So we have to be a little bit careful. Mia is correct, but I want to make sure that we're clear that it's not as necessarily as simple as furthest left, furthest right, because they're two separate sections. Yeah, so because this first section really goes from infinity to -3 with a bracket, and the second section starts at -3 with a parenthesis and goes to positive infinity. This is really what we're seeing in a picture. But if we go from everything negative infinity to -3, including -3, and we start right after -3 and go to positive infinity, that's the same thing as just going negative infinity to positive infinity, right? Where there's really no break in x values. There. What's the range going to be? Mia? That's also correct. At this point, its y-coordinate is negative and positive infinity. But since those 2 points aren't connected, we need to be a little bit careful. The only points that, or y values are missing would be the stuff between these two. But those points or those y values are also used in those two locations, so we're good. All the y values got used. Is everybody okay with that idea? Yes, sir.
We're going to backtrack a little bit.
Nope, that's okay.
So it has infinity, like main range, because it's a function.
No. The infinities on the domain and range have to do with the upper and lower bounds for the function. So you could certainly have an infinite number of points and the domain and range never involve infinity. So for example, the domain would be -3 to +1. And the range would be -3 to +2. And that's an infinite number of points, and neither the domain or range involve an infinity. Do you see the difference there, Joe? Okay. So it has to do with where the left, like the lower bound and upper bound are for the domain or range. So for the domain, the lower bound is the furthest point to the left. And the upper bound is the furthest point to the right, which is here. And then we had to be a little bit careful because they weren't connected in between. We have a gap. But it was okay because this first section used everything up to -3, including -3. And this second section starts at -3 and uses everything after. So all the x coordinates really get covered. Is that okay? And we can make a similar argument then for the range with the y coordinates. Jane.
So if those points, like a 3 and -3 are the same, then would you have to do the union interval?
You could, I mean, if you wanted to even here, if you wrote, that's not incorrect. I would still mark that correct. It's not the simplest version of it, but that's still correct. Okay? So I would not mark that wrong. Just, I think that's the kind of the question you're asking, right? So again, we'll write the simplest version more often than not. Doesn't mean that's the only thing that could be considered correct. And if you're, if you want clarification on that, certainly stop me and ask and be like, could I have also written this as an answer? And I'd be happy to let you know like what I think of that answer and whether it's right or wrong or some like partially right or how right it is. Okay? Yeah, of course. Maddie.
So those 16 of them shared -3, you'd be able to write it with the u or without it,
So yeah, so if this point here was also open, you would have to write it as two separate union in the middle. Because that point is included, -3 is used somewhere, we can kind of write it all as one big interval. Does that, okay? That's what you're asking, right? Okay. If I don't get your question quite right, like please stop me and be like, no, what I really meant was, whatever. It's important that I'm answering these things. And I hope I'm doing a good job to this point. We're okay? These are good questions that you're asking. These are important questions to ask, right? It lets me know you're thinking hard about like trying to figure out how to do these and make sure you understand. So if you need to ask clarification questions and like these what if questions, that's okay. All right. So now let's do the, I'm going to erase some of these marks. Positive, negative, and 0 parts. Okay. So how many positive sections do you see in this graph? 2. Good. Should see this one, and then this one. Everybody agree? Okay. That first positive section begins -5, 0, but we only care about the x coordinate, which is why you all said -5, which is fine. And it ends at what point? -3, 4, but we only care about the x. Now let's decide whether we need parentheses or brackets. If I look at the point, -5, 0, is that point above the x-axis? No, so we get a parenthesis. If I look at the point -3, 4, is that point above the x-axis? Yes, so that gets a bracket. Everybody's good there? And then we'll do our union, and we'll write our other interval. Our other positive piece begins at what point? 3, 0, but we only care about the x, and it ends at what point? Positive infinity, but we only care about the x coordinate. So the infinities always get a parenthesis. And then if I look at 3, 0, is that above the x-axis? No, so it gets a parenthesis. Everybody happy there? Okay. How many negative parts do we see? 2, right? We have this part here, and then that part there. Everybody agree? Okay. So for the first negative piece, what point does that begin at? Negative infinity. And where does it end at? -5. Should the -5 get a bracket or a parenthesis? Parenthesis, because that point is not below the x-axis. Okay, and we move on to the next one. We begin at what point? -3, and we end at +3. -3 should get a parenthesis or bracket? parenthesis, even though that point is below the x-axis, notice that it's an open point, it's not included. That supersedes the location of the point. Everybody's okay there? Good. And the positive 3 should get a parenthesis. Okay. And now the zeros. How many parts of the graph are 0? Maddie? Yeah, that's okay. So I think people said there are 2 positive sections right there. Notice that those positive sections are points and not like a line segment, right? Because of that, the notation is that we'll use is different because that is a finite set of things. So I'm going to use the squiggly bracket notation, and I can just list the x coordinates individually. Are we okay there? Okay. Last thing we'll do is increasing, decreasing, and constant. I'm out of colors to highlight, so I'll use like green to circle the parts then, I guess, or different colors to circle the parts. Maybe we'll get some crazy colors here like purple. Well, graph, how many increasing parts do you see? 2. 2 is the correct answer. I need to include another point though, so I guess I have to make up something here. So let's say that's -4, 5. All right. And then this section is increasing. Everybody agree with that? Notice that there still is a little decreasing piece on that first part of the graph, though, right? Okay. So when I look at that first increasing piece goes from what to what? -4. Good. Should they get parentheses or brackets? Both parentheses. For increasing, decreasing, constant, remember they're always parentheses. You don't have to think about these ones. There's no trick. They're all going to be parentheses because of the way we defined increasing and decreasing and constant. Okay. The other increasing section begins at 1 and goes to positive infinity. And again, always parentheses on increasings. Yes, Mia? Yes, still x coordinates that we're referencing. Okay, how many decreasing sections do you see? 1, this guy right here. So that begins at, and it ends at -3. We happy there? Constant sections do you see? 1, this guy right here. So that begins at -3 and it ends. And again, the ends of these are always parentheses, so the open and closed of the points doesn't even matter to us there. Is everybody happy with this? Okay. Nice little review of increasing, decreasing, domains and range, positive, negative, function, not function. Little review to start. Sound good? Okay. Oh, we didn't do end behavior. We talked about end behavior last time, didn't we? Okay, well, let's do that real quick. Sorry. One more. So, end behavior is describing the direction of the arrows, right? How many arrows do I see? 2. This first arrow, what's going on? And which arrow would we call this? the left arrow. So remember, left and right involves the x's. And because we're going to the left, that's where the negative infinities live. And up and down involves the down. It goes towards the negative infinities there. Everybody okay with that? The other arrow is here. We'd say in words that this is right arrow, and it's pointing up. So again, left and right is the x's because it's going to the right. That's where positive infinities are. Up and down is the y's because it's going up. That's where positive infinities live on the y's. So there's our end behavior. Sorry, I almost forgot to do that. But this is pretty easy to do, right? You just have to be okay with the notation, which once we've done it in words, the notation is usually makes sense after we've described it in words. All right, good. So today we need to talk about Extrema at 5. Can somebody, if somebody knows it's 4, okay, let's do it then. The extreme, I should say, relative highest or lowest points on a graph so we have maxima and we have minima. Maxima is just the plural for the word maximum. Minima is just the plural for the word minimum. As you might expect, maxima refers to the highest points, and minima refers to the lowest points. And for maxima and minima, there's global maxima or minima, which is just the overall highest or lowest point. And then there's local maxima or minima, which is just the highest or lowest point in its neighborhood. So let's look at a concrete example, because this is not a very technical definition, but I think usually after 1 or 2 concrete examples, most students are like, okay, this is easy. Because again, the only thing we're really using to do something like this is our eyes, right? Oops. I want to do... There we go. So here's a graph. How many maxima do we see? You should see 2. There's one here, and there's one there. Now, the maximum on the left, is that local or global? That's global because that's the highest overall point in the whole function. Everybody agree with that? The maximum here on the right, local, because it is in its point, but it's not the highest point overall. How many minima do we see? We see 1. The 1 is that local or global? This is only local because these ends of the graph are pointing down. There are points lower than that point, right? The ends of the graph don't represent a minimum because any point you pick on one of these ends of the graph, there's another point lower than it because the arrow is pointing down, right? So no matter what you tried to say was the minimum, there's always something lower than that. So in this graph, there is no global minimum. Everybody's okay with that? And obviously there could be no global maximum. It wouldn't be hard to draw a graph that looked like that. Can you draw a graph that has neither global minimum or global maximum? As long as you have one arrow going opposite directions, you got it, right? Can you draw a graph where you have more than one global maximum? Sure you can. What if we just drew this where you have like a tie for first? Okay with that? Yes.
So then would they both be global and local, or would it be global with no local?
I would say like the global is the bigger term. So you don't have to include them both. Like being the overall highest also means you're the highest in your neighborhood, is the way I would say that. So we can have more than one global maximum or minimum, right? If I just flip the graph upside down, that's an example of more than one global minimum. Can you have infinitely many global maxima or minima? Sure. Well, what would a graph like that look like? About something like this. Now, everything in here is a global maximum, right? Because they're all tied for first, or tied for highest. So that's about as tricky as that gets. You just have to be able to pick them out of the picture. So that's not difficult, right? Especially after we've seen a couple of examples and talked about what can or cannot happen. What if we wanted to find the exact point of a global maximum or minimum? We can use our calculator to do this. So let's take a minute and let me show you how you can do that. So I'm going to show you on my graphing calculator. If you have your graphing calculator with you and you'd like to follow along, you are invited to do so. If you want to just sit and watch, that's okay. If you don't have your calculator and you're like, I would have liked to follow along, but I can't anyways because I don't have it with me, that's okay. Remember, I am recording all the lectures, so you can always go back and watch the calculator part again if you need a refresher on how to do that. Everybody's okay? All right. So, first thing we're going to do, we're going to turn on the calculator. Yes, I know that seems dumb that I'm giving instructions how to do this, but some of us, this could be the first time they've ever touched their graphing calculator. The on button is located in the lower left-hand corner. We're going to press the on button. So most of us should be at a screen that looks something like this, right? Let's take a moment and describe what it is exactly that we're going to ask our calculator to do here, just so we have an overall picture of what the process is going to kind of look like. We're going to want to give the calculator a graph, and then we're going to ourselves visually identify where the maxima or minima are on our graph. And then we're going to give the calculator a range of values and say, okay, between here and here, find the maximum or find the minimum. And the calculator will go through and actually find the location of that point to like a lot of decimal places for us. Is everybody okay with that idea? Okay. So first thing we need to do is to get something into graph. To do that, to graph anything, we're going to press the y equals button, which is located in the upper left-hand corner. Now I have something typed into my y equals menu already. That's what we're going to graph here in just a second. You should check your calculator though and make sure that none of your y equals spots have anything in it. When I say any of them, I mean scroll all the way down to the bottom because there's like 10 spots. There's some off the screen that you can't see. You should scroll all the way down to the bottom, make sure there's no gobbledygook in there. If you do see something in there that you need to get rid of, just use the clear button. It'll wipe the whole line. After you've checked that, go back up to Y1, and I'm going to write here on the side exactly what we're going to type in, because you can't see the whole line on my calculator screen. If you're looking for the symbol for the X is located right here next to the alpha button. That's that green button on the home. So right next to that is the X. The parentheses are above the 8 and 9. And then your addition and subtraction symbols are here on the right. Make sure that you use the subtraction symbol and not the negative symbol. The calculator regards these as two different things and will give you an error if you're trying to use a negative sign where you mean to use a subtraction symbol. I'll give you guys a moment to type that in, those of you that are following along. Okay. What I want to do next is I want to generate a graph of this equation. So to graph this, the calculator needs to know, like, over what values do I need to display a picture for? What should be the, if I'm drawing an x-axis, where should my x-axis start? Where should it end? Where should my y-axis start? Where should it end? Now, more often than not, we want to use kind of the same values probably over and over and over again, unless we know for a fact that, like, I'm using specific data and I've generated something and I know kind of the values in which I should be picturing this. More often than that, we're probably going to want to do something just kind of basic, like starting at -10 and going to +10 on both the x and y axis. The calculator has that option programmed into it. So if you press the zoom button, which is in the middle of that top home row, and you see there's a bunch of options, the one that we're going to be interested in is called Z standard. That's option 6. So you can scroll down and press enter on Z standard, or you could just press the number 6. And what that's going to do is it's going to graph that function on that standard window that goes from -10 to +10 on both the x and y. Does anybody have an issue graphing? You should have gotten something that looks basically identical to this. If we look at this graph, I see one maximum and I see one minimum. Everybody agree with that? They're both locals, right? There is no global on there. So let's say we want to find this maximum first. Sound good? To access the commands that you can use on a graph, we're going to press second and then the trace button. So the second button is that blue button. Notice above the word trace in blue is the word calculate. So pressing second and then the trace button is going to open up the calculate menu. This calculate menu contains functions that you can do, well, calculator functions that you can do on your graph. If you look at that list, which one sounds like the one that we're going to be interested in if we're looking for a maximum? Maximum. So you can scroll down and select the maximum command, or you could just press the number 4. When you do that, it returns you to the graph. But notice in the lower left-hand corner here, we're asked a question, left bound with a question mark. You'll also notice that you'll have a cursor on your graph likely viewable. Mine happens to be at 0, 0. Yours might not be at that same location. It could be somewhere else. What we need to do to answer this left-bound question is we need to move that cursor so that it's on the left side of the maximum. It doesn't matter where on the left side, but it has to be left of that maximum. So I'm just going to use the left or right arrow and move my cursor so it's somewhere left of that maximum. And then I'll press enter. You'll notice at the bottom the question is changed. It now says right bound. So I'll just move my cursor somewhere to the right of that maximum. It doesn't matter where. So that looks good. And then press enter. And then the third question it asks us is for a guess. The guess doesn't matter as long as it's in between your two guesses. So I would just leave the cursor where it is and just press enter again. Technically speaking, if you supply a good guess, it takes less time to find the maximum. But when we say less time, we mean like microseconds, like compute cycles on a computer. It's not even worth changing and making a better guess. Just press enter where you're at. So this outputs then, it tells us the maximum and it tells the x and y coordinates. So if I wanted to write my answer to 3 decimal places, the x coordinate I would write then would be -1.120, and the y coordinate would be 4.061. And that's our local maximum. Mia?
Is that usually what we use for decimal points?
Yeah, I'd be clear in the instructions about how I'd want you to do the rounding, but that's usually a pretty safe bet. It gives me enough decimal places to know that you didn't just, that you actually had to do this to get it, right? You can't just like make up or like guesstimate or use the trace function and get close. You won't get the rounding quite right. Is that okay? All right. Do the same thing now, but find the minimum. Right? So we have to press second and trace to go back to that calculate menu. And this time we're going to use the minimum command. And we're going to do that same left bound, right bound guess. So that's the same set of instructions. Take a minute and try to do this if you have your calculator. If you don't, just kind of hang tight. You can watch what I'm doing or whatever, if that helps. So when I did it, I get 1.786 comma negative 8.209. That's my local minimum. Any questions about this? Basically, the calculator did all the heavy lifting for us, right? To actually find the location of those maxima or minima is not a trivial question. And in fact, until you take a calculus course, we don't have a good method for finding those maxima or minima. That's not an approximation or a special case. But in calculus, you'll develop a method in which you're able to find those maxima or minima without having to rely on a piece of technology or making an approximation, which is nice. Okay, so that's all I have to say about Extrema, which is not too bad. Next thing I want to talk about is transformations. So I'm going to ask you guys to remember back to geometry last year. You guys talked about transformations of figures. Do you remember the 4 different types of transformations you would have talked about? Well, let me get you started. One of them was a translation. That's where you pick up the figure and you're just going to move it left or right or up and down, but the orientation of figure doesn't change. The scale, the size of the figure doesn't change. The only thing that changes is its location. Yeah? But the orientation could change and the location could change. Berg. What's the first name? Natalie. Thank you. Reflection is one of them. Excellent. So the orientation will change and the location changes, but the size still stays the same. Evan, do you have the last one? Dilation is the last one. Very good. In a dilation, the size of the figure changes. It gets bigger or smaller. The location changes because it's now bigger or smaller, right? The vertices have to be in, well, some of the vertices at least have to be in a new location. Like if one of them's the origin, like that doesn't change, but the rest of it would. Good. Okay. Do you remember in geometry where you draw like a transformation map that described how the ordered pairs were changing? So for a translation, xy went to the point like x minus y, or x minus h, y minus k. You kind of remember that. A rotation, we're not worrying about an algebra course because it's quite complicated to rotate a function about something, so that's not something we're going to worry about. A reflection, the only two reflections we're going to worry about, you remember there was many types of reflections you could do in geometry, across the x-axis, or a reflection across the y-axis. And then I think there's a couple of different kinds of dilations. We're always going to just consider a uniform dilation where the same factors apply to the x or the y. Does that all kind of ring a bell from geometry, I'm hoping? At least looks a little familiar, even if you didn't remember these maps or the specific names of things. Like, once we start talking about it, I just need it to look kind of familiar. Everybody's so far so good? Okay. So, what we're going to talk about now, because more often than not when we are in algebra, we're not describing our function with a set of ordered pairs, right? We're typically going to be using a graph, or we're going to be using an equation, but we don't like to use sets of ordered pairs because most of the things we deal with have infinite ordered pairs in them. So it's kind of an inconvenient notation for us, right? So let's say we have the function y equals f of x. I'll refer to this as the parent function because this is going to be the thing that we're going to transform. So our transformed function is going to look something like this. These coefficients, this a, b, h, and k, all have some effect on what type of transformation is occurring to our function. So let's discuss what those are. So A has two effects. So if that's our reflection across the y-axis. If A is positive, there's no reflection. But A also does something else. Greater than 1. This is a dilation. I'm going to refer to this type of dilation as a vertical stretch by a factor of A. I'm going to refer to this type of dilation as a vertical shrink. Okay. Similarly, if B is negative, this is now a reflection across the. If B is positive, though, there's no reflection. If the magnitude of B is greater than 1, we have a horizontal stretch factor of B. I don't know why I wrote it. If the absolute value of B or the magnitude of B is less than 1, we have a horizontal shrink by a factor of b. So notice the a's and b's are in charge of two of our transformations, right? They're in charge of dilations and reflections. So now let's do the h's. If h is positive, we're going to go right h units. And if h is negative, we're going to go left h units. If k is positive, we're going to go up k units. And if k is negative, we're going to go down k units. So the h and k are in charge of the translation, right? Okay. So let's say that we want to describe the transformation in words on the function f of. If our transformed function is g of x equals negative 3 times x minus 2 squared plus 5. So we should start by identifying our values for k, because we're going to use the numeric values of those and the list of criteria we just made to decide what type of transformation is going on. What is our value for a? So remember, what we're saying is, or what we're referring to is this, right? Where we have our original and our transformed. Evan, negative 3. So the a is the coefficient. If I look at the something squared, the coefficient on our something squared is negative 3. Does that everybody see that? Good job. What is our value for b? What was that? I heard somebody whisper it and they were right. Joe? It's not 5. Did you have your hand up?
I was gonna say one.
And 1 is correct. So notice that b is the coefficient inside the function. Do we see any coefficient in? No, and because that coefficient is multiplying, coefficient is multiply. If you do 1 times anything, it's just the same thing as though it not being written there, right? So if you don't see a b, it's 1. Good. What's our value for h? Maddie? 2. Note that it's positive 2 and not negative 2. Even though there's a negative sign here, there's a negative sign in our general form. So the h's are always the opposite of the sign you expect. So it looks like it's a negative 2 written there. The h is always a positive 2. It's always the opposite. Okay with that? And our k is 5. Is everybody happy there? So now if I go back through our criteria, I can determine what each one of these things do. Since the a is negative, I have a reflection across the x-axis. Because the magnitude of A is greater than 1, I have a vertical stretch by a factor of 3. Since the B is 1, I have no reflection on the y. Oh, I'm sorry, I flipped those around, didn't I? Sorry. The A is the reflection on the y. The B is a reflection across the x. Sorry, guys. And because the magnitude of B is 1, that's neither greater than 1 nor less than 1, so this does no dilation. I should probably say horizontal. Since the H is positive 2, we're going to go right 2 units. And the K is positive 5, it's going to go up 5 units. So that's what I would expect the new graph to look like. Is everybody okay with that idea? Again, the hardest part is just kind of figuring out the values, but you can just do that by basically using your eyes, right? Okay. So, in general, we can find our transformed points by using this map. So for example, if we have f of x is equal to x squared and g of x is equal to that same thing we had before, we know here that a is negative 3, b is 1, h is 2, and k is 5. Our map as 2, negative 3 times y plus 5. So instead of trying to find points directly from my transformed function, what I can do is I can find points on my original function and then transform those points individually. So for example, in f, I have the point, say, negative 2, 4. It's on y equals x squared, right? Because if I plug those values in for x, I get that corresponding value of y after I square the x value. So what I can do then is I can transform those points using my map. And then I have negative 3 times 4 plus 5. So my new point would be 0, negative 7. Or here I have 1 times 0 plus 2, 0 plus 5. So my new point is 2, 5. And the next one, I have 1 times 2 plus 2, comma, negative 3 times 4 plus 5. That's going to give me 4, negative 7. So if we plotted both of them, let's see, I'm going to need to actually make some real coordinates here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. All right. So I have negative 2, 4, 0, 0, positive 2, 4. So this is my original function. And then my new transformed function, I have 0, negative 7. I have 2, 5. Oops. One more there. And then I have 4, negative 7. Looks like this. So if we look at this function, it appears like it's flipped upside down. That's the reflection across the y. It appears skinnier. That's the vertical stretch. If you take a look at the vertex, that's been moved to the right 2 units and up 5 units, which is exactly what it is that we're seeing. Right? The description that we wrote before matches exactly what we've seen. So, the idea here is that when we encounter these new types of functions, we can learn a lot about any transformation of that function by studying the simplest version of it. Okay? So the big takeaway here, the things that you want to make sure we remember, the function map will be excellent to remember. That'll be useful. You'll use that. And this description of the general form for a transformed function, and then what all the A, B, H, and K do are the 2 big takeaways from this. Okay with that? Okay. So, today I'm going to put in homework assignments involving extrema and end behavior. All you're going to be doing with those is using your calculator and then looking at some pictures and writing the end behaviors. I'm going to put in an assignment for transformations, where I'm going to give you some points and a transformation, and you have to transform the new points. On Thursday, you guys are aware this is a work from home day. Okay? My plan for the work for home day is I'm just going to give you the this was the last topic I really wanted to worry about, so I'm going to give you the review for the chapter to work on at home. I'm going to put that up today in the content library and up on PowerSchool, so you can start on that even now if you wanted to. When we meet back next week, we'll take some questions from the review. We'll talk about what the test will look like and how that'll work. If we have some time, we'll start the next chapter a little bit, and then we'll probably do the test the following class that week. I have to look at the calendar to figure out what days those are, but that's kind of the plan at this point. If we need to adjust, we can adjust, but that's at least in my head what I think what the plan I think would be. Is that okay with everybody? Okay. So I'm done, so you guys can relax here.